Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, it's a pleasure to welcome Fabio Martinelli. This topic of Glauber dynamics for the Ising model is now one of my favorites, but I really first learned about it from Fabio's lectures in St. Fleur in 1997. So I'm very delighted that he's going to tell us some of the latest developments today. Thank you.
So thank you, Yuval, for this invitation and super nice day here at Microsoft Research. Okay, so I'm going to tell you some, exciting new progresses in this topic. Okay, so general overview is, so we will talk about Gibbs Sampler or Glauber dynamics for a spin model. I assume that many of you have heard about this topic here. And okay, so there is this general dichotomy that if you consider the mixing time, say optimal mixing time like n log n, or say poly in n bounds on the mixing time are possible if there is some kind of what's called spatial mixing property for the system, that roughly speaking means that faraway region behaves sort of independently. So the interesting question that has been open for many years with very slow progress is what happens and which tools are available to analyze the mixing time when this spatial mixing is not really present. So for example, that's a typical situation when the system has sort of multi-phases structure. So there are bottlenecks and so on and so forth. So really to understand deeply the evolution of the Glauber dynamics really requires to a very detailed analysis that in many situations is not today possible. Okay, so, but I want to talk about a case study. So the case study is the Ising model on a finite grid L by L. Okay, so the box L by L is the gray one. So those are the inner vertices. Outside there are boundary vertices, and at each vertex is attached a variable that it takes value plus or minus 1. This variable is conventionally called spin. Okay, from physics, but it's really jargon. Okay, so sigma y is the spin attached to an inner vertex, and on the boundary vertices there are it is one could fix some spin configuration, and in order to distinguish from the inner spin, it's called usually tau. Okay, and those are imagined to be frozen once and for all, so assigned to a certain value plus or minus 1. According to what one really wants to study. Okay, and okay, so then given an assignment of the internal spin sigma and given the boundary spin that tau fixed once and for all, so the energy of this assignment is given by minus the sum of the product of spin where xy, where x tilde y simply means that xy are the endpoints of a bond inside the gray box. And then there is also an interaction or energy term that is related, so connects the spin to a boundary vertex. So of course the sum is only along bonds that connect the inner box to the boundary. Okay, then okay, so the probability distribution over the spin configuration is called the Gibbs measure, but sometimes this is a scary word. Simply is so the probability of a spin assignment, and I put a tau here just to remember that there are these boundary conditions outside, is proportional to exponential of minus of beta is some positive parameter that you tune. Okay, the energy of the assignment. Okay, that's just a standard called Boltzmann weight. Okay, so a quick review of what is known for this model in two dimension is that there exists a critical value. So is one of those exactly solvable model on the grid. So beta critical takes this value such that if beta is smaller than this critical value, then essentially the boundary spin are irrelevant. There is a strong decay of correlation among the spin. And, well, irrelevant means the following, that if you look, for example, at the distribution of the marginal of the spin at the center of the box, and you send L, so the side of the box, to infinity, whatever you put around the box does not produce any bias. Okay? So instead, if beta is larger than beta critical, then the boundary spin have an effect even when L goes to infinity. So, for example, if they are all plus, they put a bias towards +1, and if they are -1 by symmetry to -1. Okay, so it's clear that correlation are not really decaying. Okay, so there is an appearance of infinite long order range. Okay, so if beta is at beta critical, then there is a a big story with SLE, and so probably here is one of the best places in the world. Okay, so what we want to look at is Gibbs Sampler or Glauber dynamics, which is just the standard one. So so in discrete time, you pick uniformly at random one of the inner vertices, and you resample the spin, namely you put a new value ±1, extracted from the distribution at x, given the current configuration around you. Okay, and so this actually is possible to compute very simply explicitly. Okay, so in continuous time, exactly the same, except that you do this resampling at the vertex x according to a Poisson clock of mean 1. Okay, so in this talk I will choose the continuous time version. So in mean each second a spin gets updated. Okay, so the mixing time is for this Gibbs sampler. You start from some configuration, you compute the distribution that you get at time t, you compare it in total variation to the equilibrium distribution, so the Gibbs measure, and then you take the worst case over the initial condition, and you ask how long do you have to wait in such a way that this is, say, less than 1/4. Okay? Okay, so quickly all the results. So if beta is less than the critical value. What? Oh, this. Oh.
These are two different people.
Okay. Yeah. So I'm sorry. Yeah. Okay. I'm always mixed up with. Okay. And anyway, so if beta is smaller than the critical value, then mixing time is order log L, which in discrete time means L log L, so optimal. Okay, and actually, so recently there has been a very beautiful and sort of surprising result that it's possible to prove the cutoff phenomena, namely really to pin down the mixing time log L with a sharp constant plus a window that is log L. Okay, and that was a beautiful paper by Eyal and Alan here. Then again, by the same group of people, if beta is critical, then mixing time, as expected by physicists and a number of simulations, is polynomial. It's very interesting that the missing bit to prove really to attack this problem comes from SLE. And I mean, okay, they get, of course, polynomial with certain power that is not really the power predicted by physicists, but still this was, an open problem for many, many years, quite nice. So instead, if beta is larger than the critical, and there are no boundary conditions, namely that tau spin are absent, okay, then the mixing time is exponential with a sharp constant that depends on beta, L in L. So you see that there is this critical values is a signature going from log L to exponential L going through polynomial. Okay, that was the picture so far. Okay, so what's the role of the boundary condition when beta is bigger than beta critical? So without boundary condition is exponential in L, as we just saw. And so instead, if the boundary condition, they select what is a phase. So you have to, if you look at the energy of a spin assignment, then without boundary condition, the spin, they want to be equal. Okay, so in order to minimize the energy, this means either all plus or all minus. Okay, so if the boundary condition tells the system you should prefer plus, okay, for example, in the...
If you just go back one slide, you really feel a bit uncomfortable, very uncomfortable with the first bullet. We just show cutoff phenomena wherever there's strong spatial mixing, and Fabio and the group of people showed this holds all the way to the critical.
That's history. So.
It's giving the proper credit.
Okay. When I was young. Okay, so the idea is that if the boundary condition, they select a phase, okay, so they sort of break this multimodal, actually bimodal structure of the Gibbs measure, and therefore you expect that if you almost restore unimodality, the Gibbs sampler should mix much faster. Okay. A few years ago, there has been rigorous result for this problem by Alistair Sinclair, Dror Weiss, and myself. On trees, or a student of mine, Alessandra Bianchi, on hyperbolic graphs. And the result is that actually the mixing time goes back to optimal. Sorry, this is copied, so this should be L, but anyway. Okay, so what's happening in two dimension when beta is bigger than beta critical, and say the boundary spins are all pluses. Already Fabio told you something about this problem in 3 dimensions at 0 temperature. Okay, but it's something like that. So if you start from all minuses, so in the wrong situation, then you should go to mostly pluses, so the correct equilibrium. So there should be like a bubble, and the exact form of this bubble is unknown. Okay, that shrinks under the pressure of the surrounding pluses. Okay, and one expects a polynomial mixing time. Okay, so that is a super rough picture. If you really look at the boundary of this bubble of mostly minuses, is really some line, some contour that separated pluses from minuses. Okay, there are overhangs and so on and so forth. Okay. So the key problem is really to understand the evolution of these interfaces under the Gibbs sampler. And until recently, the best bound, I proved many years ago, is that the mixing time is exponential of a little bit more than root L. Okay? And actually that was proven for beta much larger than the critical value. Then there was some other work with much less sharp result, but beta just bigger than the critical value. Okay, so still very far from polynomial. Okay, better than exponential in L, but still very far from polynomial. Now the key tool, because I want to get as quickly as possible to the newest result, is block dynamics, or today's I would actually use censoring, the Perez-Winkler censoring. So censoring means the following in 2 words. that so if you start from the maximal configuration, namely all pluses, and you want to go down to equilibrium, if you decide to reject certain update at certain time in certain region, okay, that you have to pre-assign without knowing the actual evolution, then you will actually be further from the equilibrium than if you would have accepted the moves. Okay, so this tool of censoring opens the way to sort of saying, first I run the dynamics here, then there, then again in another place, and so on. And so you can sort of try to guide the Gibbs sampler towards equilibrium according to some sort of some scheduling that you sort of prepare in advance. Okay, so the scheduling here would be the following. So imagine that you split your box into long rectangles, and the width is a little bit more than root L. Okay, and you start from all minuses. So suppose now that you run the dynamics for a very long time only in this initial rectangle in such a way that after this time you are at equilibrium in this rectangle. So the boundary conditions are plus, 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 and minus outside because you started from minuses. Well, so the minuses must be separated by the pluses by a line that is very badly drawn here, but this red line really separated the pluses from the minuses. The key point is that this line behaves like a random walk condition to come back at 0. Okay, so if you believe that, and this is really a big part in equilibrium probability estimate to prove that it really behaves like a random walk, then clearly the fluctuation above this horizontal line are of order root L, and therefore they are so the red line must be very well below this midline because I added this epsilon here. Okay, so after the mixing time of this rectangle, you have put essentially above equilibrium, so the correct almost plus case. And then if you start now again from the second rectangle, this like violet rectangle here, on top you will see basically pluses, which is exactly the same situation of the first one. So you can start to repeat. Okay, and so if you repeat, you bring down this red line now to this level, then to another level, and down. Okay, and then you have reached equilibrium. Okay, of course this is super sketchy, but exactly this is the line of proof. So how long does it take? Well, essentially you have to do this many steps. So how many rectangles there are here? That is a little bit then root L. Okay, and each one takes you a time. Okay, now you have to make some mixing time estimate for the Gibbs sampling in this rectangle. For example, you could use canonical path, the canonical path techniques by Jerome Sinclair, and this tells you that the worst is exponential of the shortest side, and therefore that explains this result. Okay. Okay. So what we really need to improve in order to go, beyond this L a little bit more than root L is the mixing time of a rectangle plus, plus, and minus. Okay. So in the S of S approximation, so S of S approximation is if you replace the contour separating the pluses of minuses, which have overhangs and all sorts of complications, by really like a discrete, so the graph of a discrete function, okay, like that. So with Alistair Sinclair, we analyze this problem, and so you can apply David techniques, so the coupling introduced by David to study Lozenge tilings and so on. And so you plus other work, and you get to polynomial, and with almost optimal power, namely 2.5 instead of 2. But okay. So, but really the question is that the real problem is that the true contour doesn't look like that. It's more complicated, and so the problem is still open. So, okay, so a year ago with Fabio, we made the first step forward the deeper understanding. And okay, so the first idea is that if you want to improve the bound, you have to accept the fact that you are not able to work with, fixed plus or minus boundary condition, but you have to accept to work with random boundary condition. So need to consider random boundary condition tau with some law, okay? And there are two cases. So case A, so I say that the law of this distribution is, okay, so I order the spin from, so north, east, southwest, okay? And so I say that P is like plus, 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 okay? If the marginal on, say, the northern side or eastern side and so on is as positive as the Ising plus phase, okay? So as a reference distribution which is obtained by the taking a box with plus boundary condition, sending the box to infinity, you get a certain distribution. This is what is called the plus phase. So is as positive as the distribution obtained from this plus phase. Yeah.
Just more
But if it was really in the plus phase, then say the north and the east side would be dependent on each other. So
Yeah.
exactly.
Just the margin. So I just ask that the marginal here is bigger, is above. Yeah. And minus means that you are more negative than the minus phase, which is just the opposite. Okay. Okay. So the theorem that we prove is the following. So you fix a little error epsilon and stay very well away from the critical point, so beta much larger than this critical point. Then in both cases, A or B. So P, now P here is the probability over the random boundary condition, and this P is either more plus than everywhere, or is 3 plus, more 3 pluses and less 1 minus, okay, so in the southern side. Then the probability that the mixing time, so the mixing time is, of course, depends on the random boundary condition, so it's a random variable. So the probability that this guy is bigger than exponential of L to this little power is so small. It's very surprising that actually this result is almost optimal, okay? So it's not optimal because of these two. And the reason is that years ago, Ken Alexander proved, and Yoshida and Alexander, they proved that if you have exactly plus, but at the corner you put a little bit of minuses, this many minuses around the corner, then the mixing time becomes exponential of this length. Okay? And so the probability that you put this guy is a negative exponential of this length, and so we are pretty close. Okay? And then we also proved that if instead you start from all pluses, then you mix it very fast. Okay, so I would like to give a sketch, which is, of course is sketch with many sketches in between. Okay, so the main idea is to bound the mixing time. So whenever I write this plus, plus, and minus, I really mean that they are random, and their distribution satisfy the monotonicity that I mentioned. Of course, an extreme case is when they are exactly all pluses or all minuses, but this is only an extreme case. Okay, so the main idea is to bound the mixing time via an iterative procedure, essentially doubling the scale. Okay? And the main problem is that at each step I have to reproduce boundary condition on smaller region that satisfy the assumption of being more plus or more negative than the plus or minus phase, okay, first. Censoring is absolutely essential, so I'll show you that first we will tell one part of the space to do something, then the second part to do something else, and so on and so forth. Now, so in the recursion, we need some time scale that we want to prove that is not more than exponential of L to the epsilon. And this time scale, for example, we choose the following definition. So we take the average over the variation distance starting from all pluses or all minuses of the Gibbs sampler from the equilibrium distribution. And we ask the time, and we wait for the time such that this average is less than a small constant delta. And in the recursion, both delta and t will depend on the scale and will change from going from L to 2L, 4L, and so on and so forth. Okay? And of course, we have to keep track in such a way that the final result is the correct one. Okay. So, in the approach, there is an easy bit and a hard bit. Okay? So, let me describe the easy bit. So we want to go from, well, actually, the recursion is L is L to the 2L plus 1. Okay? Okay? So that's the precise sequence. Okay? So we have a rectangle 2L plus 1, and the side is 2L plus 1, root plus epsilon. Okay? So first thing is the following. We want to estimate the mixing time of that in terms of the mixing time of a rectangle which is 2L plus 1, the base, and instead is only L to the power 1/2 plus epsilon on the vertical side. Okay, so these two rectangles, A is this guy and B is this other guy. They are 2L plus 1 and L to the 1/2 plus epsilon on the vertical side. Okay. Okay, so let's say that we start from all minuses, and we have mostly plus here and mostly minus here. So we start from all minuses, and first we run A. Using censoring, we can only run A. So since we start from all minuses, the spin in this region are frozen equal to minus, so it's like to have minus outside along this line. Okay? So we run A for exactly its mixing time, so in such a way that the equilibrium here is on average at this delta from its equilibrium. And now, okay, so there is a line separating the minuses here from the pluses there, and this line is this red guy. And this red guy is not able to reach this dash line, simply because this red line behaves like a random walk, fluctuation are root L, and this dash line is a little bit more than root L. Okay? Then, so essentially here, then, so I have some random boundary condition here at the end of this time, but the distribution of this random boundary condition is more positive than the plus phase because it has plus here, plus here, plus here, and on the red line, on the outside of the red line as pluses. Okay? And so it's more positive, so it's a good distribution for us. Okay, so we can then run the rectangle B, okay, for exactly another amount of time, on scale for this rectangle. And then we have reached equilibrium.
Something very fishy here, because but I can't quite put my finger on it. Below the red line you have minuses, and you let it mix, and now you're more positive than pluses.
No.
Above the red line.
Above the red line you have pluses.
Above the red line you have pluses. Yeah. So all what I need is that the spin along this line, this dash line, right, are random, but the distribution is more positive than the plus phase, which is correct because I have plus, 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 and outside this line, so this line is separating pluses from minuses.
It's because the dotted line is higher up than the solid line.
Yeah. That is crucial.
So for instance, below on the solid line below the red one, you're more minus. Right?
Yeah, of course. Yeah.
I mean, it sounds as first as if you
got
something fanatic, because you started off more negative and you ended up more.
We can. Okay. Okay. Then we have to study the mixing time with random boundary condition of the good sort of a rectangle which is 2L plus 1 on the long side, but only L, 1/2 plus epsilon on the vertical side. And we have to estimate this mixing time in terms of the mixing time of a rectangle which is only L times L. Okay? So if we are able to do that, then likely we are able to establish a recursion, a mixing time going from L to 2L plus 1, and then we can solve the recursion. Okay? Okay, so here comes the second idea. Okay? And this is the heartbeat. Okay, so let me try to explain how it goes. Okay, so so one is tempted to run first. So we start from all minuses. So there are minuses here, minuses there, and minuses around. So and pluses on top. So you are tempted to run the central rectangle, but then the central rectangle will equilibrate, but the separation line of pluses from minuses, so this red line, being a random walk, will stay very close to the top and not to the bottom, and therefore the distribution over this pin here will not be plus as required to do then left or right. So we are in trouble. Okay, we are not reproducing the correct boundary condition. Okay. Well, the main idea is to exploit anomalous fluctuation of the interface. It is true that most of the time the interface will be very close to the top, but there is a little bit of chance that sometimes the interface will actually go down and then up again. If that occurs, then you have to imagine that here are all pluses, and therefore the distribution here now will be very much plus. Okay? So the probability of going down being like a random walk is just exponential of minus L to the 2 epsilon, if you, because it's a random walk on time L, and you have to go level root L to the 1/2 plus epsilon. So that's the probability. So very intuitively, okay, one would like to run the central rectangle many times, many its mixing time. How many? Well, this number of time, okay, in such a way that in one run you will see this large fluctuation. Then, as soon as you see the fluctuation, then you run the left and the right until you equilibrate. Yeah. Okay. So, okay. So certainly that is forbidden. Okay, because censoring cannot be applied to your, depending on your current configuration. That's very attractive, but it's forbidden. But it's definitely forbidden. Okay. Still in the yeah. So many times one goes back to that, but so it's still doable actually. Okay. In the first version of the paper, there was a super messy chapter with this idea. So the way out is instead less natural but more elegant, and is the following. Okay, it is true that here in the bottom we have minuses. By brute force, I change many minuses here, and I replace by plus, and I start to attract the random walk. Okay, so please, come here. Okay, and the question is how many. Okay. Well, okay, so this is a beautiful simulation by Yale and Alan. Okay, so suppose that I have minuses here. Okay, so sort of the blue dots. Okay, and I put a little bit of pluses here and pluses on top. So there are two possibilities. Either the pluses stay close to the top and a little bit close to the bottom, or the pluses, they go down, they reach their friends down on the bottom boundary, and they form two contours, one to the left and one to the right. Okay, there are two possibilities. would be very nice if the second possibility is the likely one, because then on the vertical line, that is one of the side of the two vertical rectangle, then I see now pluses exactly as I want. Okay. Okay. So the cost for a random walk to go down this L to 1/2 plus epsilon is, as we saw, is exponential of minus L to the 2 epsilon. However, the reward of killing this extra contour is proportional to exponential of the length of this region. So if I take this length much bigger than L to the 2 epsilon, the reward is more than the cost, and then this situation will be more likely. Okay? Yeah. So the probability that this random walk goes down to this is, so the cost is like that. However, the reward of eliminating this, this contour, this little contour with respect to this situation, is that. Yeah, it's something like that. So if delta, if this region is more than L to the 2 epsilon, it's better to come down, because so the total cost, say length, is more convenient for you. Okay. And of course, there is a huge part of the work that really tries to prove that. Okay, because this is not really random walk, right? Yeah. So the final result is. So the final result is. So we say that this is true if this. So if at time t you have on average distance less than delta from equilibrium for all distribution of the random boundary conditions that are more positive or more negative than the plus or minus phase, and then so the easy and hard bit prove that is true, that this assumption implies this other one. And basically, so I'm not writing the exact recursion, but basically the error that you pay in variation distance is like a constant of the previous one, okay? And the time that you need in the second instance is like the old one and times this little exponential, okay? Then, of course, you need an input, okay, for the recursion, okay? And the input is you go down to a scale which is L to the epsilon, and there you apply just a canonical path, and you make some terrible estimate. Okay. Okay. So the recursion is okay. So then okay, we were already very happy, but yep.
I didn't understand. What about the method lets you sort of plant the pluses there?
Sorry.
What lets you plant this interval?
Oh yeah. Sorry. Okay. Why? Yeah. Maybe. Yeah. Actually, this is an important. Okay, so this is a sort of an abstract is a simple calculation. You ask yourself, what is the mixing time with say all minus boundary condition here, or what is the mixing time if instead of all putting all minuses here, I put this delta of pluses by brute force. Okay, so then it's easy to see that the ratio between the two mixing time is at most exponential of the size of delta. Okay, so you decide that you work with delta, but you pay a price, of course, which is exponential of this distance. Yeah. Okay. Okay. Then okay. So then when Alan and Eyal visited Rome, we start discussing and. So it came out that it's possible to improve, and so to improve to the point that the mixing time is quasi-polynomial. Okay, so originally we wrote exponential of log square, but then we learned that it's better to sell like a quasi-polynomial. So I'm ready to adjust, and quite surprisingly, we can prove this result. Not for very large beta, but for any beta bigger than the critical one. So, and I guess that's the last. Yeah. So the last slide, or almost, yeah. So the key new ideas. This really there is very much to say. Maybe they can provide later the detail. Okay, so there is a new recursion scheme. First of all, still essentially doubling the scale. Okay, but organized in a different ways. Then there is a new analysis of the contours of this interface separating pluses from minuses with really very precise estimates that are like random walk-like. Okay, so proving that really behaves for all what we need, essentially really like a random walk. For example, we are able to prove the following, that so in this situation, I think that this is remarkable, but oh.
Higher up.
Oh, here?
It says L to L. Oh,
yeah, okay, so if you put, say, plus, minus, 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 so there is some line now separating the pluses from the minus. So, for example, one estimate that we need is to prove that the probability that this line is all above the horizontal line, so level 0, that this probability is at most is at least an inverse polynomial of the scale, and okay, that was absolutely essential. And actually, we can prove that, and actually, we can really prove that is exactly as for random walk bridge, which is apparently really non-trivial. And what is surprising is that there is using this random line representation, we can get this bound up to the critical point excluded. And so the bottom line that in the new recursion, the mixing time gets worse by a polynomial in L factor, and since there are only log L step, then you get this quasi-polynomial. So that's the last slide. So originally we had a rectangle that were of a length like that, and here there was this length to the power 1/2 plus epsilon. So that's the current length in the recursion, and instead here we make it thinner. Okay, so a large constant root of this. Okay, so that would be the scale of the typical fluctuation of this red line. And then in order to get this side away from this red line, we put a root of log of the final scales where we want to get. Then of course we need super precise estimates that are really exactly like random walk to get the easy and hard bit and as in the previous work, and then we get this quasi-polynomial. Okay, so forecast for a polynomial according to Ayala is 10 years, and I don't know. Okay, thank you.
You drop everything else for this period.
Yeah. Okay, thank you.
Questions or comments? Anyone see an easy way to get it down to polynomial?